welcome to the third part of bioremediation and bioaugmentation. We're now going to talk a little bit about bringing the additions of the contaminants and the bacteria together in situ, the requirement for biodegradation to occur. So again, to remind you of this little cartoon, we have a fairly intelligent microbial community. They realize that if they're able to degrade this chemical, they can produce little bacteria. And that's really their purpose. They're not terribly interested in eating this chemical for our benefit. They're really trying to produce progeny. So what they're doing, of course, is taking the contaminant and eating it. Well, what we're doing is adding then some salt and pepper and maybe some sugar. That is electron acceptors, nutrients, things like that. So that's our job, is putting the right materials on the plate for Mr. and Mrs. Bacteria to go at it. Here are a number of references to this section on moving things around in the subsurface. Again, I'll point out this last one, the textbook by Payne et al., where they really do, I think, get remedial hydraulics right on. So how do we bring about contaminants and bacteria together in situ? The commonest way is to add water that contains whatever we need, electron acceptors, nutrients, things like that. So we have a contaminated aquifer. Let's assume we have dissolved contaminants that are mobile. So we might inject water containing some remedial chemicals. There's a well, there's the injection, and we inject. Hydrogeologists know how to inject water in wells. We do that all the time. But we have to remember that when we inject the water, all it does is displace the water that's there. There's very little mixing. The dispersive mixing that occurs is relatively minor at the fringes of the water we've injected. So we inject more water, and again, we simply displace contaminated water. We get some mixing zones, and we keep doing that until we get all our water in, and then we're waiting for degradation to occur. Well, our job, of course, is to make the bacteria happy. That bacteria is happy. Why? Well, it has some contaminants to degrade, and it has some remedial chemical, just in that area where dispersion has done the mixing. What about this bacteria? Well, they're not very happy at all. There's contaminants, but no remedial chemicals. So we just have to keep injecting. What about that bacteria? Well, it's got lots of remedial chemicals, but it's got almost no contaminants. The contaminants are being pushed aside by the injected water. Simply injecting water into the subsurface is a rather ineffective way to try to remediate mobile contaminants. We're just pushing the contaminant away from the water we're injecting, and we need those two waters to mix. What about the case where, in fact, we're trying to remediate a source zone where there are residuals or highly sorbed compounds? Well, I think the prognosis is much better. In that area, the bacteria, in fact, would be happy. Why? Well, the contaminant is still present in the form of residuals that are dissolving. And the bacteria is likely to live right at that interface between the dissolving residual and the water that contains the remedial chemicals. So for mobile chemicals, injecting water does very little. For immobile chemicals, it may in fact be a very good way to get the remedial chemicals to the contaminants. So a number of people have tried to use fairly passive techniques. We've seen before that passivity saves money. And so if we can do things like add oxygen to the subsurface without a lot of effort, without adding water, in fact, it probably is cheaper and maybe just as effective. So there's a number of experiments that have been done and a number of remedial technologies that involve releasing chemicals into a well and then using the natural flow systems to do the mixing of those chemicals with the contaminant. So if you put a fence of wells in the subsurface, as the groundwater goes by, perhaps the remedial chemicals inside those wells are released and they mix with the water as it goes by, and we've solved our problem. We've added the remedial chemical, in this case oxygen or hydrogen-making chemicals, to the subsurface and got them mixing with the contaminants. Well, the question is, how close do those wells need to be? Some consultants believe something in the order of 3 to 5 meters apart is very good. I don't think that's borne out by much factual information, however. So, certainly these ways of adding chemicals to wells gets chemicals in the well water. The question is, does it get it into the contaminant plume? A number of experiments have been done by consultants at real field sites, adding oxygen by things like the oxygen emitter, which diffuses oxygen into a well, or ORC, which is a solid emitting substance. And their experience or their observation is if they put that in a well in a contaminant plume, the oxygen effect, that is the oxygen itself or the oxygen that's being transformed into CO2 by degradation of benzene, for instance, is found at quite large lateral distances away, 3 to 5 meters perhaps away in a transverse direction from the point of release. And therefore it would take one well to affect a fairly large area. For people that have done these experiments, in this case I think it was emitters, but we could use oxygen releasing chemicals, which we just stick into a well in a sock arrangement. It's a solid material. Put it in these wells. In this case, Doug McKay and his colleagues put the wells very close together, 0.5 meters apart. And the difference between this site at Borden and the real field site is the number of monitoring wells. So these are multi-level monitoring wells, placed extremely close together. What did they find? Well, there was no contaminants here, so they were able to trace the oxygen that was added. The oxygen was found in a very narrow range down gradient. Remember, transverse dispersion in aquifers is very weak. This is exactly what you'd expect to see, that there's minimal transverse dispersion or transverse mixing. And so the plume emanating from the treatment well is a very long, narrow plume. And it'll take a long time before the very weak transverse dispersion mixes the contaminated water that's bypassing the well with the remedial chemicals that have been released through the well. So we're aiming then for a practical solution, but it's conceptually wrong. Limited transverse dispersion means that the distance between the wells needs to be very close together if we want to impact the plume in between the wells. And Payne and that textbook captures that very well. Have a read of this. Transverse dispersivity cannot generate a wide swath of reagent coverage from a small single distribution. So we're not talking about recirculation well or injection extraction dipoles here. What they're thinking of, I think, in terms of a typical two-well system is to attack contaminated water by injecting remedial chemicals in one well and drawing the remedial chemicals through the aquifer to the other well. The problem is that as you do this, if the contaminant is mobile, it's moving as well. So all you're doing is injecting clean water with remedial chemicals, and it's chasing the contaminated water. Contaminated water is extracted. Often that water then is brought to the surface and treated, and then recirculated with the extra addition of nutrients or oxygen or whatever. Turns out most of that treatment actually occurs above ground. It's an ex situ treatment system. So this is essentially a very sophisticated pump and treat system if the chemical is mobile. If the chemical isn't mobile, this might work because we're flushing remedial chemicals past a fixed contaminant, and as it dissolves from the residual, it's picked up and degraded in place. So again, for mobile contaminants, this probably is not a very good in situ treatment train. There are other ways to take advantage of the limited dispersion we have in the subsurface, and that makes use of the fact that there's more longitudinal dispersion, that is, dispersion in the direction of flow, as opposed to transverse. So if we have a plume, let's look look down on this plume, so we're looking at the transverse and longitudinal directions, groundwater flow from left to right. Let's put a well in and inject a slug of clean water that contains the remedial chemicals. So we inject for some period of time and then stop injecting. Well, that water is picked up by the groundwater flow and transported down gradient. Then sometime later we inject again. So we're injecting these little slugs. As they move down gradient, mixing occurs by longitudinal dispersion. So that is, at the front and the rear of this slug, we get mixing. The remedial chemicals are spread out, they're diluted, but they're spread out. So later we do another injection, and that slug moves down gradient. Eventually that slug disperses enough so that there's essentially always some remedial chemical and some contaminant available at every spot over time. And that's exactly what we need to promote bioremediation. These bacteria don't mind a fluctuating level of remedial chemicals and contaminants, but they really don't like being turned absolutely on and absolutely off. So these slug injections have been shown by Rick Devlin that they can create a down gradient bioreactive zone which is consistent, which is present all the time. The difficulty, of course, is this is somewhat down gradient. In Borden, in the experiment he was doing, it's a matter of a few meters. And so if you have a few meters of travel distance in which this mixing can occur, then this might be a good approach. And it's less work than continually injecting. It's a pulse injection. The idea is to create a down gradient reactive zone where there's always remedial chemicals and contaminant present. So again, transverse dispersion can't be relied on. Longitudinal dispersion is of some use, but it'll take some travel distance. We could also use various walls to do things. Here's another view of pulsed injection using an injection wall. In this case, you can either make a trench, you could engineer a trench of permeable material so that if you inject remedial chemical at this side of the plume, you can draw it across to this side of the plume. Or you can just use the natural aquifer. Using the natural aquifer will get you flow lines that go further out. But if you use a high hydraulic conductivity contrast, you can get this slug of water completely across the plume and quite narrow. After the first injection, we wait a while, repeat the injection. The first injected slug moves down gradient, some longitudinal dispersion, some mixing. Further down gradient, there's more mixing. Further down gradient, there's essentially adequate mixing. And this would be where the biological treatment would be occurring. Up here, if you look at the bacteria fixed, it's going to see some remedial chemicals with contaminants. Then as this part of the slug passes them, they'll see some remedial chemicals but no contaminants. Go back into a phase of adequate material, both contaminant and remedial chemical, so bacteria start up again, but then they're shut down because of the lack of remedial chemical. Whereas down here they have this continually, and the plumes are now completely overlapped. And that's exactly what you want. Happy bacteria. So those are some ideas on how to deliver remedial chemicals. It's not easy. It's a job of a hydrogeologist. It's a good challenge, and so I think it's something that we can do. But it usually requires a little bit more thought than a single well injecting chemicals over some period of time. So we'll finish off this lecture in the next part. Till then, goodbye.